Hello and welcome, dear students. The topic of today's lecture is Introduction to Hydrological Modeling. Dear students, let us first understand what system approach means in hydrology. The system approach to hydrology conceptualizes water resources, particularly groundwater, as an interconnected and dynamic system governed by fundamental physical laws. This framework provides a comprehensive methodology for analyzing water movement and predicting the potential impacts of changes of the hydrological system. The foundation of this approach is based on two key scientific approaches. Number one, conservation of mass, which says that water is neither created nor destroyed. This is a fundamental to understanding hydrological system. This concept is captured in continuity equation, also known as the hydrologic equation, which states that the difference between inputs and outputs correspond to the change in the stored water. Second is the energy and flow. Water movement is driven by variations in fluid energy. It naturally flows from regions of high energy or higher hydraulic head, which is a measure of fluid energy, to regions of lower energy in accordance with Darcy's law. In hydrology, systems are classified as depending on their interaction with the surrounding environment. Based on the hydrological systems and subsystems can be divided into open versus closed system. So far as open systems are concerned, open systems are those systems that allow both mass and energy transfer. The hydrological units such as lakes or aquifers are open systems because water enters in the system in the form of recharge and leaves the system in the form of discharge. Evaporation through the system boundaries. So far as the closed system is concerned, closed systems are those systems where mass remains constant, but this system allows energy transfer through its boundaries. The global water cycle is often treated as the closed system because the total mass of water on Earth remains constant, while solar energy enters the system to drive processes like evaporation. Now let us discuss about lumped versus distributed systems. So far as lumped systems are concerned, those are the models which treat the system as a single unit or black box. They focus solely on inputs and outputs over time, ignoring internal spatial variations or the details of the physical processes occurring inside. They typically utilize the simply continuity equation that we already talked about. So far as the distribution systems are concerned, these models account for spatial variations within the system. They divide the steady area into grids or meshes to simulate how properties like pressure or hydraulic conductivity and processes vary from point to point. Now, to connect the concepts of the system to the modeling, let us first understand what is modeling. A model is a simplified representation of complex natural systems that are often too large or complicated to study directly. In hydrology and hydrogeology, models provide quantitative frameworks for analyzing water movement. Models are the most reliable way to synthesize field information and predict consequences of future changes. The modeling process follows a systematic workflow starting with conceptual understanding of the water system. The first step in developing a quantitative model is formulating the conceptual model, that is a qualitative description of the flow system that summarizes known information and functions as a hypothesis. The conceptual model determines the mathematical formulation by establishing system boundaries, underground layer properties, water flow directions, and water entry exit points. creating the conceptual model inquiries parsimony, including only processes necessary to meet study objectives. Now, let us discuss about types of hydrological and hydrogeological models. Once the conceptual model is established, the water system can be formally analyzed using several categories of models. So far as the physical models are concerned, or we can call them as analog models. Physical models involve constructing scaled down setups in a laboratory to observe and measure fluid flow directly. This system includes tanks or columns packed filled with porous material like sand, where hydraulic heads and flow rates are measured. Analog models rely on similar physical processes to mimic the natural groundwater movement. Before modern computers, early hydrogeological problems were sometimes modeled using the flow of electric current or viscous fluids to simulate groundwater flow patterns. Now, if we discuss about the mathematical models, these models translate the physical understanding described in the conceptual model into a quantitative framework using equations derived from physical laws. These models are classified by their approach to underlying physics. These models utilize empirical or statistical equations which are formulated from existing data to assess the system response to various inputs such as how precipitation can lead to rise in water level. They do this with explicitly quantifying the underlying physical processes or properties of the system. An example is using an artificial neural network, that is ANN model, to predict water levels based on historical weather patterns. Now, if we just talk about the process-based models, process-based models favored for most serious investigations which rely on the principles of physics such as the conservation of mass and the basic law of fluid flow, that is the Darcy's law, to describe the water movement mathematically. Now, if we just talk about the numerical model are the primary tool used today for real world problems because they can handle complex geometrics, three-dimensional flow and systems where the properties vary widely, that is the heterogeneous media. Since the problem cannot be solved directly, the physical environment is converted into an approximation by discretizing it, dividing the continuous space into a finite number of discrete points or nodes or small volumes, that is cells, where the equations are solved iteratively. The main types of numerical methods used are finite differences. This method divides the problem area into a regular grid, usually consisting of rectangular cells or blocks, that is a widely used FD code, that is mod flow. The entire modeling process, from abstracting the complex natural world into a conceptual model to executing a finalized numerical model, is comparable to creating a sophisticated global positioning system GPS. The fixed rules of physics act as a permanent map. The conceptual model is the initial hand-drawn route, and the complex numerical calculations finds the fastest, most probable route while acknowledging the traffic conditions, means the arrival time will only be approximate. A conceptual model is fundamentally a simplified quantitative description of a water flow system that synthesizes everything currently known about a specific site or area. It acts as an evolving hypothesis or mental construct about how the water system functions. Conceptual models are necessary first step in any quantitative water study, as they establish the foundation for designing any formal mathematical or numerical simulation model. The purpose of modeling in hydrology and hydrogeology is to use a systematic quantitative approach to understand, describe and predict the behavior of water systems. Because groundwater systems are often complex, vast and hidden from direct view, models provide the reliable description of a system for informed decision making. The main objective for most models is to predict or forecast the status of groundwater with respect to groundwater withdrawals or climate change. For example, models are used to predict how such changes will affect water quantity, quality and movement. Groundwater flow models are essential tools because they solve for quantities that cannot be fully measured throughout the entire field setting, specifically determining the distribution of fluid energy in space and time. Once heads are calculated, associated essential information such as flow rates, water budgets, flow paths and travel times can be derived easily. So far as supporting monitoring and data collection is concerned, models are also providing insights into the value and relevance of field measurements, aiding in better resource allocation for future investigations. Models can also be used to determine which location and type of future data collection activities would be most valuable for reducing forecast uncertainty. This enables cost benefit analysis to optimize monitoring networks and guide fieldwork efforts. A model offers a quantitative basis for rigorously compiling and making sense of diverse field data such as water levels, flow rates and hydrogeological properties. Ultimately, the goal of modeling is to construct the most justifiable and reliable description of a groundwater system for quantitative analysis and forecasting of the consequences of action like pumping. Now, let us discuss modeling approach and uncertainty analysis. The entire process of analyzing and predicting how water systems behave is known as modeling approach. This approach follows a systematic workflow that begins with establishing a clear purpose, developing a conceptual background and then translating that framework into a mathematical form that can be solved. Because natural water systems are often hidden from view to too complex to study directly. So, numerical models provide the most offensible description for informed decision making and forecasting. Now, let us discuss the core stages of the numerical modeling approach. They are discretization, calibration, validation and uncertainty analysis. Discretization, as you are very aware about, is the process of converting the continuous reality of a physical system into a simplified representation consisting of a finite number of discrete components. This step is essential for using numerical methods to solve the governing equations of water flow. The physical space of the study area, which is the flow domain, is divided into a network of small volumes called cells or elements and points which are called nodes. Now, so far as the importance of the scale is concerned, the size and spacing of these discrete blocks are critical because they determine the resolution of the model's output. If flow paths, that is the movement of the water, or hydraulic gradients, that is the hydraulic head, the slopes driving flow vary widely in a specific area, fine discretization within a small cell size is required to accurately capture those details. If we just talk about the parameterization, which is the method used to describe the complex real world ground conditions using a simplified set of numbers that a computer model can understand. Because the earth is spatially variable, we cannot measure every single inch of it. So, groundwater modelers must convert their knowledge of ground into specific inputs for the computer. A computer model sees the world as a grid of squares or mesh of triangles. Parameterization is a step where you assign specific properties known as parameters to these grids or meshes. Since the real world is infinitely complex, parameterization forces the modeler to simplify reality, which can be achieved through zonation. The area to be modeled is divided into different shapes or zones based on the geology. Every point inside a single zone is given the exact same value. This keeps the model simple. Second is, instead of distinct zones with sharp borders, the modeler assigns values to specific points known as pilot points. This allows the computer to calculate smooth transitions between these points. This creates a smooth change in properties across the map, which often looks more natural, so parameterization is crucial for. Now let us discuss about calibration. Calibration is the most critical stage in the entire modeling workflow, serving to assess the modeler's performance and establish it as a reliable representation of the field system. Fix the model to match the reality. Here, groundwater model parameters are adjusted until the model's result match what they observe in the field, like water levels in a well. Now let us discuss the boundary conditions. The mathematical definition of the boundary is a fundamental part of designing a hydrogeological model, as these boundary defines the limits of the system and control how water moves within it. Boundary conditions specify the head, that is the water level, or the flux, that is the flow rate, along the outer edge of the model or at the internal source and sinks. There are three primary types of mathematical boundary conditions used in the quantitative hydrogeology and hydrology. First is the specified head boundary, which defines the specific head boundary. The specific head boundary fixes the water level, that is hydraulic head, at the chosen points along the model boundary. This condition is most appropriately applied to represent substantial perennial bodies of water such as oceans, major lakes or rivers, where the water level is presumed to remain constant and is not expected to be substantially influenced by activities within the groundwater system, such as pumping or changing in recharge. The major drawback is that a specified head boundary acts as a potential influent source or sink of water. If the fixed head value does not accurately reflect reality, for example, trying to simulate a small stream as a constant water source, it can lead to inaccurate simulated heads or fluxes. Second is the specified flow boundary. The specified flow boundary fixes the precise volumetric flow rates, that is the fluxes, across the boundary. The actual water level, that is the head, at these boundary points is then calculated by model and can change as the simulation progresses. The condition is used to represent flow that is known to enter or leave the system at a constant rate. It is also used to simulate defined flow rates from pumping or injection wells. Newman condition is used to represent the recharge, also generally using specified flow conditions to represent recharge is preferred over attempting to use specified heads for the water table. It can represent horizontal flow across the perimeter of the model. Newman conditions can also be used to represent no flow condition, a condition where the flow rate is set to 0. This is typically used at boundaries adjacent to impermeable materials like compact bedrock or along hydraulic divides like streamline where water flows parallel to the boundary. The third is the head dependent boundary. The head dependent boundary defines the flow across the perimeter or internal feature based on the difference between a user defined external water level and the water level calculated by the model near the boundary. This relationship is governed by the conductance factor. The conductance factor represents the ease with which water can pass through the interface material like streambed sediments. This condition is highly adaptable, used for features that dynamically exchange water with the aquifer, including streams, lakes, wetlands, drains, and springs. The head dependent boundary allows the simulated boundary flows to be automatically updated as the model's calculated head changes, making it ideal for transient simulations where flow conditions fluctuate. This boundary can be used to mathematically extend the model domain to link the simulated flow to a distant physical feature, such as a large lake located outside the modeled area. Additionally, it is used to simulate water loss due to evapotranspiration from the water table. Now, let us briefly discuss the governing equation. The process of converting a conceptual model of a hydrological system into a mathematical model involves using equations based on physical laws. At the core of this process is governing equation, which provides a mathematical representation of water flow within the system. The exact form of this governing equation is determined by physical factors being modeled, such as whether the flow is steady or changing over time, and whether it occurs in saturated or unsaturated materials. Therefore, the governing equations fundamental to hydrological and hydrogeological modeling are the conservation of mass and Darcy's law. All process-based models of groundwater flow are derived from two basic principles, that is the conservation of mass, that is the water balance, and Darcy's law. Now, let us have a brief and quick introduction about different types of modeling softwares. We use analytical models or analytical element tools like GFlow. They are fast but assume the ground is pretty uniform. For complex real world problems, we turn to numerical models like ModFlow, which is the big industry standard. It divides the area of interest into grid or blocks to calculate flow. If you have complex geology, FAFLOW model is used, which uses a flexible mesh of triangles. Instead, to track pollution, we link these to transport codes like MT3DMS. Finally, we usually run these through user-friendly interfaces, that is the graphical user interfaces like Visual ModFlow or Groundwater Vistas to make building the models easier. This was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.